Hello and welcome to NHP's webinar on the essentials of field switching and sensing. My name is Thomas Krajinovic, and I'm a commercial engineer for NHP Electrical Engineering, specializing in safety sensing and hazardous area equipment. Now, this will be the first of two webinars specifically designed to inform you on sensors, from identifying a product, understanding how they operate, having a look at what applications are possible, and how to get more out of your sensors for diagnostic and preventative maintenance. Now, you'll see in the window that there is a Q&A section box there, and you're welcome to post any questions you have at any time during the presentation, and these will likely be answered as we continue through the presentation by our support staff. We'll also have some time at the end of the presentation to address these questions or any additional ones that you have at that time. Now, in this session, we will be exploring the difference between contact and non-contact sensors, how to identify various sensor types and how they operate, and we'll look through some applications and sensor selections. So what we will cover today will be an overview of the common types of sensor technologies that you'll come into contact with and that NHP supply. Now, this presentation will be a fundamentals on these sensors, and there will be some level of detail on this. However, although you will not learn everything in today's session, you will have a better understanding and appreciation of how these sensor technologies work and what you need to know when considering different technologies and making your selection. So the presentation will cover contact versus non-contact sensing, and we'll just go through the basic differences between the two. We'll then look at product identification, where we'll look at what types of sensors you commonly see, and we'll quickly highlight how they look. We'll then go over the concepts of operation, and we'll break down the sensor types that we've looked at and how they function, and then we'll highlight any important notes or concepts on these sensors. And lastly, we'll look through applications and sensor selection. So we'll just review an application example and look at suitable sensors for the applications that we're looking at. So first off, as obvious as this might be, it's just important to note the differences between contact and non-contact sensor technologies. So contact field switching and sensing technologies rely on the physical object or material you wish to detect coming into direct contact with the device you're using. So the object that you wish to monitor needs to actually physically interact with the sensor in some way, shape or form and exert a force onto it. Now, non-contact field switching and sensing technologies rely on the sensor using another medium, which it monitors to indirectly detect the material or object you're looking at. Now, the sensor is free to monitor these objects and materials from a distance using the medium in order to trigger detection. Now, when we say the sensors use another medium, these include things such as light, sound, magnetic fields, also measuring and sensing of inductive fields and capacitive fields. So it's important to be aware of these two differences. And it's also important to note that contact sensors are mechanical in design and operation and are generally they have no solid state components. So they're slower in operation due to the physical need to move, and they have a physical life expectancy. Whereas non-contact sensors, they're solid state, they have faster detection and switching capabilities, and generally exhibit longer life and less maintenance and replacement if the sensor is selected and placed correctly for the application. So moving on to how you can identify these products. So here we can see some of the common contact devices that you'll find in industry. So we have limit switches on the left, and these consist of a body with an actuating arm known as an actuator, which comes into contact with a physical object. Now, these actuators can vary in design from the roller seen here through to a spring whisker type actuator. And next after that, we have electronic and electromechanical level detection. So the electronic versions are at the top, and the first device after the relay uses conductive level detection using the stainless steel probes with the level control relay. And to the right of this then, so this is a non-conductive level detection device using the photoelectric level sensors with a level control relay. Below that is the electromechanical version, and this is a more simple device, which are a basic pre-wired cable with a float device and a counterweight. Then next after that to the right, we have pressure sensors, which effectively look like either a plastic housed or metal housed box or cylinder, which have a number of either dials, buttons, or even potentially a screen, and connecting points for piping from a pressurized system for connection. Now, you can clearly identify these units due to their physical differences, but this isn't always the case, and specifically not so with non-contact sensors. Now, looking at non-contact devices, so some are easy to identify between each other, but this isn't always the case. So the specific type can be harder to determine just by looking at some of the sensors, so you would normally need some further information about the application. Now, on the left, we have photoelectric sensors, and we can see there's a few different types, and these will all have a sensor body that is either rectangular or cylindrical with a glass or plastic panel on the front to allow light to exit and enter the sensor. So the three common types shown here are through beam, retroreflective, and diffuse. Next, we have magnetic sensors. Now these have a few different form factors, however, they're easily identifiable again, as they have one device with contacts and a cable, and a second actuator, which is used with the sensors, and this is the magnet. And then after that, it gets a little bit more tricky. We have inductive, capacitive, and ultrasonic sensors. Now, these can all be in similar form factor, and it's not easy to determine the type on the appearance alone. So the application and how these sensors are used will give you a better understanding of what type of sensor it is. Now, this will come to you as you understand how the sensors work, and we'll see this in a little bit within the presentation. Now, it's just important to note that, again, understanding the application is important for all sensors, and knowing this, the material or the object to detect, and possible install locations is all critical for selecting a sensor correctly. So now let's have a look at exactly how these types of sensors work. So limit switches have an actuator that needs to be moved by the object or material that is wanting to be detected in order for it to work. So the actuator is connected either directly via a shaft or plunger to the contacts internally, or through something like a spring internal to the switch. Now, physically moving the actuator moves this shaft and plunger down to activate the contacts. Now, the actuator style can affect where the limit switch is placed, and you wouldn't be able to use the roller lever style limit switch in the exact same position in this case. That's the one in the bottom right there. Now, in regards to the contacts, there's one important aspect to be aware of, and this is the type of contact within the limit switch. So the two types that you will see are both snap and slow action. So with snap, all contacts change state instantaneously at the point of actuation, while with slow contacts, they make or break at separate points. Now, it's just important to note here that these do not specify a time delay, and you actually can't for a physical device like this, as it depends on the speed of the physical object or materials being detected and hitting the actuator. Another important thing to also note is contacts are all actuated regardless of how the actuator is moved, so left or right for the roller lever. There are, however, some limit switches like the neutral position limit switch from Rockwell that actuate two separate sets of contacts based on the direction the actuator is moved. The left triggers one set, right triggers another. Now, the advantages of using limit switches are selected and placed well, only the object will trigger it. So if it's out of the reach or it can't touch anything else. There's obviously versions as well that are positively guided or have positively guided contacts in them, like the safety ones. So welds can be broken just by the act of actuating. The disadvantages, however, are they can be defeated if they're not placed well, and they can also be damaged by physical objects in abnormal operation in the sensing area. And they're also mechanical in design, so they're not good for fast repetitive operation because they will fail. Now, looking at electronic level detection, we have two methods here. So conductive level detection, where the probes are placed within the tank, which will then detect liquid present by measuring the resistance between the stainless steel rods when conductive fluid is between them or when the liquid is absent to the rods compared to a reference. Now, the relay then interprets this in order to determine if the water level is low or high or absent and alters its output contacts accordingly. Now, it's just important to note that this technology requires the liquid to be conductive and clearly non-volatile when exposed to the probe, so you wouldn't want to use it on anything like petrol. Now, non-conductive level detection uses a photoelectric probe that internally produces a light within the tip of the sensor, which is reflected back into the sensor when in the air. So once this sensor is submerged in liquid, the internal light produced is refracted through the glass and into the water. The control relay then detects this and acts accordingly. Now, the advantages of electronic level detection are you have discrete levels for detection by cutting the probes down or placing them the photoelectric sensor at the correct level. And the relay also recognizes detection and you can fine tune the sensitivity of this. Now, the disadvantages, however, are the conductive probes can't be used in small tanks where there's not much difference between the high and the low level. Obviously, for conductive, you need the liquid to be conductive. And generally, rapid water fluctuations can cause nuisance tripping. Also, chemicals within the liquid can damage these devices or impair readings. Now, looking at the simpler electromechanical level detection device, being a float switch, now these rely on the presence of liquid directly affecting the float and forcing the end with air trapped to rise. The counterweight then acts as a way to set the level. So within the end with the float, there is some conductive material that moves with the float to trigger the contacts. Now, this type of detection may be required if certain chemicals are used within the liquid, which may affect metal but not plastics, or more importantly, if the liquid itself is non-conductive. Now, one important thing to note is you do not want to use this where debris is in the liquid and it can block the float, so you need to know the application. Now, the advantages of this device are they're simple and easy to use and install. They're chemical resistant to a degree, but you still need to obviously double check what chemicals you're using. And they're slightly more robust against water fluctuations, provided there's no large swells within the tank. The disadvantages are debris can prevent actuation, so it can block the float. And again, you can't use these in small tanks where there's not much difference in high and low level. You wouldn't be able to detect that effectively. Now, last to cover for contact devices are pressure switches. So they function by being directly connected to the pressurized system through piping. The pressurized fluid then pushes against an internal bellows. So with the electromechanical pressure switch, an internal mechanism controls the set pressure that the contacts will react to and change state to once the pressure is reached and drops below a set point. Now, with solid state pressure switches, the pressure changes are measured electronically and output transistors activated based on the programmed settings. Now, when being set, you ensure you set maximum pressure rating for the contacts to cut out and select a differential which indicates how far below your set point you want your contacts to cut out also. Now, the advantages of using pressure switches, you get to directly monitor the pressure in your system, and they're fairly simple to install and use. Disadvantages, however, are that chemicals may not be suitable for the bellows type that you have, and you can't take a one-size-fits-all approach. You need to ensure the pressure range of the tank is detectable by your pressure switch, and it's not too much for your switch as well. Now, moving on to non-contact sensors. So inductive sensors are used for fast detection of metal objects and materials over a very short distance. Now, the operating principle is based on a coil and oscillator that creates a magnetic field that propagates around the sensing face or face of the sensor. Now, the presence of a metallic object in this field causes a dampening of the field. So changes are identified by an internal circuit that changes the output of the sensor. So normally it's a discrete transistor output. Now, these magnetic fields are typically only sensitive over the millimeter range, so 2 to 40 millimeters. And the actual operating distance of the sensor depends on the object's shape and size and the material. So you prefer a flatter, larger surface pointed at the surface face, and different materials interact differently with the magnetic field. So metals that are magnetic or ferrous are easy to detect as they will interact with the magnetic field of the sensor and dampen this more. So you won't lose much of the advertised sensing range, if any. While metals that are non-magnetic or non-ferrous are difficult to detect due to the weak magnetic field and interaction, so it shortens the advertised sensing range. Now, this reduction in the sensing range is known as the reduction factor or correction factor, and there are some charts that show common metals and the effect. So these reduction factors help determine what reduction in sensing distance will be experienced when certain metals are used or trying to be detected. So the application and metal being detected needs to be considered. Now, there are two types of inductive sensor designs which affect how directed the magnetic field is from the sensor face, which can help with surrounding metals. So these are labeled as shielded and unshielded. Now, shielded, you have a metal plate which surrounds the core internally and concentrates the electromagnetic field to the front of the sensor face. Now, this will slightly reduce the sensing distance, but it allows for flush mounting within the metal surrounds or within metal surrounds without false triggering. Unshielded is the opposite, and you have a slight leak of magnetic field just outside of the sensor sides. Now, the advantages of using inductive sensors are the sensor will ignore anything that is non-metallic, so dirt, water, mist, cloth, plastics, anything provided the layer isn't too thick or more than the sensing distance. It ignores the color or finish of objects, and they're solid state, so they're fairly resistant to vibration and other environmental factors. Now, the disadvantages, however, are clear in the fact that they only detect metal, they have a very limited sensing distance, and it detects all metals within the sensing range. So, provided they are not affected by the reduction factor, that is, so you need to consider any nearby metals during installation that might affect the detection. Now, capacitive sensors are used for fast detection of metallic and non-metallic objects and materials over a short distance or through other materials such as glass or plastic. Now, it's important to note that although these can be used to detect metal, in most applications inductive sensors are preferred in that case, but it's still possible. Now, capacitive sensors operate by generating an electrostatic field which reacts to changes in capacitance, which is caused when a target enters that field. So internally, when the target is outside the electrostatic field, the oscillator is inactive. As the target approaches, a capacitive coupling develops between the target and the capacitive probe. Now, when the capacitance reaches a specified threshold, the oscillator is activated, triggering the output circuit to change states. Now, these interactions are typically only sensitive over the millimeter range again, like inductive sensors. So the advantages of using capacitive sensors: you have the ability to detect both metals and non-metals, the ability to detect solids, liquids, or granular material, and the ability to detect material through others such as glass and plastic. The disadvantages, however, they have a short sensing distance again, and they're not able to detect through metals. So you'll be able to detect the metal itself, but if it was a metal container, you would only be able to detect that and not the material inside of it. Now, magnetic sensors are used in circumstances where you'd like to detect an object and can attach an actuator to it while you have the sensor in a fixed position. Now, these could be used, say, on a revolving door to count when the door with the magnet passes the sensor to count a revolution. Now, magnetic sensors contain a reed switch. So these are ferromagnetic contacts encased within a glass tube which have an inert gas. Now, when in the presence of a magnet, the magnetic elements of the reed contact attract and close. So any magnetic field can cause the contact to close, but it's important to note the magnetic field must be greater than the return force or the spring memory of the contacts. There are also some more advanced magnetic switches which do not get triggered by simple magnets and are a little bit more reliable and safer using coded magnets or RFID. However, these are generally used in safety applications as a safety sensor, not the applications where you would use something like a reed switch. Now, the advantages of using reed switches: you can add the magnet to the object wanting to be detected. It also detects through thin materials as long as the magnetic field is present. The disadvantages, however, are they can be easily defeated with magnetic fields or another magnetic actuator. Now, ultrasonic sensors are used in circumstances where you would like to detect and or measure the distance to a solid object or material, or even a finely granular material, and even a liquid. They are often used for presence and level detection in these cases. Now, they operate by producing directed ultrasonic sound pulses from the sensor face, which is reflected off of an object or material and detected back at the sensor face. Now, due to this operation, they can be used on multiple types of surfaces or materials, as mentioned before, provided they act as a solid when the sound waves hit them. So you wouldn't want to use this on acoustic foam or another surface that would significantly absorb or scatter the sound waves in directions other than the sensor face. So they can have either a discrete transistor output or an analog output to give an output signal that is directly proportional to the distance from the sensor. Now, the time it takes for the beam to strike the target and return is directly proportional to the distance of the object. So the advantages of ultrasonic sensors: you can detect most materials, as mentioned before, provided the sound waves obviously can be reflected back to the sensor. And the disadvantages, however, are it doesn't work well if the sound is absorbed. It must also view the target surface head on to work accurately, so the sound waves reflect back. And they can be affected by hot surface temperatures as well. Now, moving on to the last device we will cover, we have photoelectric sensors. So these can be used in high precision, fast detection and measurement situations where you cannot or do not want to touch the object being sensed, and you do need to have some distance between the sensor and the object. So photoelectric sensors emit their own light as the detection medium, and there's 3 different types which operate differently to each other, with some of these having their own subtypes. So before we get into this detail further, however, there are 2 important methods of operation that need to be understood. So photoelectric sensors can either work in what is known as light operation mode or dark operation mode. The light operation mode is when the output is on when the receiver can see the light, while dark operation mode is when the output is on when the light to the receiver is blocked. So it's important to note that this is due to how the sensor is designed to operate, and in some cases the sensor can actually be programmed between the two. And there are also different names for this as well. You might have heard of break switching or make switching, but they're the same thing. Now let's look into each type of these photoelectric sensors, how they function, and why we need to have these different types. So we have 3 types, as we said, the first being through beam on the left. So these are the easiest to identify and have 2 sensors. One simply emits light, which the second receiver or sensor then receives. Now these have some of the longest sensing distances available, in some cases hundreds of meters, as the beam intensity is quite high with the 2 dedicated units for transmitting and receiving. Next we have retroreflective. Now these sensors have both the emitter and receiver inside the same device, and they operate by emitting light, which when used in conjunction with a reflector allows the light to be reflected back and received. So this is used in spaces where a second receiver on the opposite side cannot be placed. Now they can be broken down into standard retroreflective and polarized retroreflective. So polarized retroreflective compared to the standard retroreflective sensors are better used for detection of highly reflective objects or surfaces, anything with a mirror finish. Now these polarized retroreflective sensors have polarizing filters internally, which help it achieve this, generally as well, achieving within the tens of meters sensing distance range. Now it's important to note that the shorter range comes as the light travels twice the distance when leaving and coming back from the sensor. And it's also important to note that the light beams actually spread outwards in all directions from the light source, and so there's less light concentration at a specific point the further out you go from the sensor. So laser sensors do help with this, however. Now, moving on to the next one, diffuse sensors. So these sensors have both the emitter and receiver inside the same device, same as the retroreflective. However, they rely on the object itself reflecting some light back into the sensor for detection. Now, these types of sensors have a low intensity beam and have a short sensing range because of this, generally around 1 meter maximum. Now, there are 2 types of these which can work on objects including matte objects with minimal reflection, such as cardboard boxes. So there is the standard unit, and then there is the background and or foreground suppression versions. The background and foreground suppression units can ignore reflections originating from objects behind or in front of the target location, as we'll see shortly. So let's have a look into these a bit further and see how they operate and their advantages and disadvantages. Now, through beam sensors have the strongest beam intensity due to the 2 dedicated units. So due to this, the advantages are they have a longer sensing distance, specifically with laser emitting sensors. There's a reduced effect caused by object surface reflections, and they're most reliable with highly reflective objects as the beam is completely blocked. And they're also better for dusty, misty, and contaminated environments due to the stronger beam intensity, which means it can handle a small level of this. Now, with this, it's just important to note that they can handle this. However, there still can be a build-up of the contaminants resting on the lens itself, which can cause problems. Now, the disadvantages of these sensors, however, are they can be more expensive as there's 2 components and they require wiring on both ends on site. They require space for install on both sides of the path of the object or material's movement. and it requires an object to block the beam completely or very close to. So objects smaller than the beam width, which do not block about 50% of the beam, might not actually be detected. The long distance units require accurate alignment as well, and there can be nuisance tripping with movement or vibration. And they have difficulty detecting clear objects. So bottles, for example, most light will pass through, and beam intensity is just too high, so you wouldn't be able to use them effectively in all situations for that. Now, standard retroreflective sensors rely on the reflector directing the light back into the direction of the light source. They're actually designed to do that. Now, the advantages are they have a lower cost of unit install, as you only have a single unit and a reflector, and this also allows for use in restricted spaces. Now, also because of the reflector design, they're easy to align. As long as you point it at the reflector, you should be okay to go. Now, the disadvantages, however, are they do have a shorter sensing distance, and that's due to the lower light intensity and the further distance that has to be traveled. Now, lighter beam intensity also means they're less resistant to dust, mist, and other environmental contaminants compared to through beam. And there's the potential to detect reflections of light from shiny objects, which can cause false detections and triggering. Now, polarized retroreflective sensors combat some of these disadvantages and are used in specific circumstances where you wish to detect shiny objects. So these function much the same as standard retroreflective sensors, however they contain internal polarizing filters. Now this means the photons making up the light that is emitted from the sensor is only in a single orientation, and the receiver of the sensor has a filter which blocks this specific orientation. So when no object is present, this polarized emitted light is then reflected off of the reflector, which acts to depolarize the light and give it multiple orientations again, so that as it gets to the receiver, some of the light is allowed to pass through. Now when a shiny object is then allowed to break the beam, it reflects the light with its orientation perfectly back to the receiver, where it gets blocked by the polarizing filters. So the advantages of polarized retroreflective sensors are the sensor can ignore first surface reflections, and they're used specifically for shiny object detection with less nuisance tripping. The disadvantages, however, are that they have a shorter sensing distance than the standard retroreflective sensors, and they can detect second, third, and so on surface reflections. The other thing is they also have even lower beam intensity due to the points of polarization, so they're more susceptible to contaminants within the environment. Now finally, looking at diffuse sensors. So these emit light and receive this after it is reflected off of an object you wish to detect. So for standard diffuse sensors, the advantages of the sensor are you only need to point the sensor at an object. You don't need a receiver or a reflector. They're easy to align because of this, and they can be used on almost any object or material. The disadvantages, however, are they're difficult to use if the background behind the object is reflective and it's too close to the object, or if there's something reflective in the foreground. They also have a much shorter sensing distance than the other sensors mentioned so far, and they have a lower intensity, so that depends on the material and how much light is actually reflected back, so they're more susceptible to environmental factors as well. Now, background and foreground suppression diffuse sensors, of course, combat some of these issues. Now, these function again much the same as standard diffuse sensors, however, they contain multiple internal receivers in an array. So the sensor then has adjustment dials, so you can tune exactly where you want the detection range to be. So in the picture here, you can see the sensor body with multiple receivers. The light that is reflected off of the object will enter the sensor and hit a particular receiver. The adjustment dial then works to tune in the range the object will be detected, ignoring reflections of anything that's closer or further away. Now the advantages of this are they ignore backgrounds beyond the rated sensing distance regardless of the reflectivity, so it won't detect something at 1 meter that's reflecting light if the sensor is only able to detect 300 mil sensing range. And they can tune the sensing range ignoring the background and foreground as well, of course. The disadvantages, however, are they're a little bit more expensive than the standards, and they're very limited. They have a very limited maximum sensing distance. Now, it's important to note that these can be used on a number of surfaces and materials. It does not need to be very reflective, but this can then, of course, affect the sensing range. Now, there are also a number of specialty sensors out there that you can see here, and these are things like sensors that can register marks and labels, color detection, luminescent particle detection, even radar sensors for movement and direction detection. Now, there are also a number of features you might find in these sensors and all of the sensors that we've gone through so far to enable them to be used in specific situations or environments depending on your application. Now, you can find sensors specifically designed for food and beverage, material handling, and sensors suitable for welding environments that are weld, field, and slag resistant, and suitable for harsh and corrosive environments. Now, there are also IR-link variants to some of these sensors and ranges which allow for communication out of your sensors for diagnostic and preventative maintenance, and we'll talk a little bit about that at the end. Now, when it comes to selection, there's a few specific things you need to know for each type of technology. So for each of the contact devices shown here, limit switches, you need to know the actuator style. Level control relays, you need to know the liquid to be sensed if there's any chemicals. And for pressure switches, you need to know the pressure ranges and connection types for the piping system. However, in all of these situations, the specifics around the application are just as critical. You want to find out and know as much as you can about the application as possible. So not only does this allow you to select the correct sensor, but it opens up the possibility for the use of another sensor that might not have been considered, because there are multiple ways to sense things after all. Now again, this slide is showing the things to consider for non-contact sensors, but the idea is the same. You want to get as much as you can about the application, including photos and details specifically if you are not present to where the sensor is wanting to be placed. Now this will help you easily select the device to replace an existing one or select a sensor based on an entirely new application. So let's look at what you might want to know about the application. So knowing the application includes things like what is wanting to be detected, what's the material, the object shape, the color, the finish, are there any wrappings or covers on the product, where is the object or material, so really an overview of where the thing is to be sensed. Is it indoors, outdoors, is it on a conveyor, what does the conveyor look like if it is on one, how does it move through the system, the area or the conveyor, how is the sensor to be placed, so where does the user want the sensor to be placed, at what point on the conveyor is something wanting to be installed on, are there any other points that are open potentially to the install. Photos can help you determine that. What is the desired outcome? So do you want to detect or count an object? Do you want a distance measurement? Or do you want more data out of your sensor? And then also, what existing systems do you have for integration? So can you just use a simple relay output or discrete transistor output? Do you need analog outputs? Or again, do you need or want more data from your sensor? Now this will give you an understanding of the application and ability to select a device for your requirements, because the application is key. So let's have a look at some of these applications. So let's look at if you were asked to detect bottles on a production line and ensure the product was present and correctly manufactured. How would you go about doing this? So there are a number of ways that this can be done, but you would need to know more. The bottle material, the color, the look, the shape, the finish. Is it shiny? Is it see-through? Is that the case all the time? What else do you need to look out for? Are there any labeling requirements? Are you just detecting a bottle? What is the environment like? Is it indoors? Is it a clean environment? Now, once you get a better understanding of the situation, you can select accordingly. So from the picture, it looks like you need to detect bottles and their fill level, their presence, if the label is present and correctly orientated, as well as if there's a cap that's placed correctly. Now you also need to detect when the label roll is low, so it needs to be replaced, and it looks like it's a indoors clean environment from what you can tell so far. So we have multiple points of detection. So the first point, we are detecting if the bottles are overfilled. Now here, this is completed via a retroreflective sensor. Now we can see that the liquid appears to block the light through the bottle completely, and there is space on both sides of the bottle for placement. Now, if the liquid level is too high, the light beam is blocked and the current retroreflective sensor detects this. But this could also be done through beam sensors. You have access to both sides. Light's completely blocked by the liquid, so if it's too high, it will still be blocked. And this would allow for some level of environmental contaminant withstand as well, more than what a retroreflective would handle. But you don't necessarily require this, as it looks like it's a clean environment and there's not a great sensing distance required. Technically, you could use a capacitive sensor as well, so provided the liquid is present at the level and it significantly changes the capacitance, you would detect this through the glass. However, and that would also ignore contaminants in the environment, but you would need to install it closer because of the sensing range. And if the bottle isn't perfectly in place, it might actually knock the sensor out of place. Now, the second point, we see detection of the label roll. So this is currently being completed via a diffuse sensor and would indicate the low level of the roll once it is out of its sensing range. Now, this could also be done via a photoelectric measurement sensor, and this will tell you how far you have left on the roll. But it might not be required, as the roll is normally changed once it gets to a set low point, and you only need discrete output then. You don't need a measurement signal. But that could also be done as well through ultrasonic sensors to measure the roll level. But again, you might not want this measurement, so you don't need that. At the third point, we can see we're detecting the label orientation before its use to ensure the label roll is correctly orientated with no issues. So here this could be done via a diffuse sensor depending on the reflectivity of one side of the label versus the other. Now this could also be done via a color and mark registration sensor. So if the label has specific marking on one side for detection, this could also be used to ensure correct orientation. The fourth point, we can see detection if the bottle is filled with liquid, and it also controls the timing of the label application. So the first sensor detected for overfill, but what if the bottle somehow missed the fill process? Now here this is done with a retroreflective sensor. Now this determines there is liquid present. If it was placed higher, it could determine that there's a minimum level that's been detected. But this again could also be done with a through beam sensor as before, and a capacitive sensor as before, but again, you might not need or want these types. It could also be done with a limit switch and with a whisker type actuator. It could detect every time the bottle passes. However, it's not as practical, especially as this would be a high speed and more frequent kind of application, and you would need to replace that regularly. Now the fifth point is detecting of the label incorrectly placed on the bottle. And here again, we use a retroreflective sensor, but this could be used via or done via a diffuse sensor. And then the final point, we have detecting that the cap is fixed to the bottles. So here you can't tell exactly what type of sensor is being used, but as we learned, it could be a few things. It could be inductive if the caps are metal. It could be capacitive. You could also use something like a diffuse photoelectric sensor, but that's not what's shown here, but you could use that. Now this just shows the knowledge of the application is critical, and there are multiple ways that you could use sensors in the same application. So for you to be able to select one correctly, you need to understand the application. Now, what if you want more out of your system and the sensor in terms of data for diagnostics, preventative maintenance and planning? So this is where you can use IO-Link enabled sensors. So IO-Link is an open standard peer-to-peer communications protocol allowing sensors and actuators to easily integrate into the connected enterprise. Now it allows you to access sensor configurations, the parameters, process data and diagnostics, allowing you to not only detect the objects or materials you have in your system, but now you can monitor your machine's health as it runs. So it allows for simple setup, commissioning and replacement of sensors while offering flexibility for current and future processes. Now the next presentation in this series will focus on this topic, showing you what IO-Link is in depth and how you can get more out of your system by using it. Now this presentation will be a live webinar presented on the 26th of September. Now this concludes today's presentation on the essentials of field switching and sensing, and by now you should have a greater understanding of contact and non-contact sensors, their limitations and advantages. So I'm now able to answer any questions that you may have or have sent during the presentation.
Thanks for that, Tom. Great presentation with some really good visuals to help showcase each sensor's functionality. So hello to everyone on the call. My name is Jack Wheatley, and I'm the Product Manager for Safety Sensing and Signalling at NHP. I'm now going to take some time to read through some of the questions we've received during this presentation, and Tom can answer them. So I've got one here, Tom. Someone's asked, can I buy an unshielded sensor and block the sides so it works as a shielded sensor? What are your thoughts on that?
Okay, so in that case, the answer is unfortunately no. So it's actually part of the sensor design internally, shielded versus unshielded. So placing metal on the sides of an unshielded sensor will cause triggering. Obviously, if you place something that's not metal, it won't be detected, but the magnetic field is still present there. So if you need to flush mount the sensor in metal surrounds or have metal anywhere close to the sides of the sensor, you would need to look at using a shielded sensor in that application, and you'd need to purchase that, select that correctly at the start of the application.
Yeah, makes sense. No problems, thanks for that. So I've got another one here that's asking, how do I accommodate for different types of liquids? So what are your thoughts on that question?
Okay, so there are a few technologies that you could use in, I guess, multiple circumstances and use it as a kind of like a default solution. But it really does depend on the application and the cost you want to associate with a kind of default solution. So, for instance, you could use ultrasonic sensors, in a lot of cases, but they are more costly, and depending on the output you want, whether it's discrete levels or measurement, there's a little bit more time involved and integration in kind of tying off that solution. So I guess for the best decision, you need to look at your application each time and consider specific things to the application. As we said, like the liquid, is it conductive? Is it just water? Is there debris or chemicals in there? And obviously what your resultant outcome is. Do you just want a discrete on and off, or do you want a kind of measurement output? So yeah.
Yep, no, totally makes sense. Thanks. Appreciate that. So someone else has also asked if NHP's got any further reading that we can forward through, or they could look up online via probably our website. Is there anything that comes to mind for yourself that we could point them to, Tom?
Well, we do have some specific sensor brochures on our website, and there is some more information from some of our suppliers that offer useful information on the differences of these technologies and how to select. So you can have a look for that, but please feel free to contact NHP if you're having any difficulties finding this, or just like to discuss, your application.
Yep. Yeah, good point. So obviously we've got their 1300 NHP phone number that puts them in touch with someone, or vice versa, the website. So I've got another question here. It's asking if they're having problems detecting an object, if it moves closer to the sensor, will this mean guaranteed detection, or will that cause problems? What are your thoughts on that?
Well, I guess it depends on the sensor technology you're using. So obviously, if you can't detect an object, it could be due to a number of factors, even one being simply out of reach of the sensing distance of the sensor. So obviously, bringing it closer in that case will assist. But you'd really have to, again, look at the application. So objects that are too close to some sensors can cause issues, some sensors have dead zones, and a dead zone is an area where just detection is not possible. So this can exist for a number of sensors, and it's due to the operation of the technology. So, for example, some photoelectric sensors, so diffuse and retroreflective, if the object is way too close, the light isn't actually reflected back properly to the receiver. It just gets kind of effectively blocked, so it wouldn't be able to detect that. Then you also have ultrasonics, because the internal transducer can't generate and receive the signals at the same time. So you need some time between that, which then translates to, I guess, a minimum sensing distance. So really any sensor that generates something, has it directed back to the sensor, can have a dead zone. So you just need to think about that. But capacitive and inductive type sensors don't. They still detect the changes, no matter how close it is to the sensor.
Cool, thanks for that. Makes sense. Definitely a big one to look out for, the dead zone. So we've probably got time for one more question before we close it off. So I've got one here that's asking, reduction factors, are they all the same across all sensors and metals?
So no, actually, the reduction factor that we saw in the slides previously, they're all specific for a certain manufacturer and I guess sensor range. It depends on the design of the sensor itself. So you would need to look to the manufacturer and the sensor you're looking at to get the correct reduction factor for that.
Cool, thanks. Yeah, so with that being said, I think that brings us to the conclusion of the webinar. Is there anything you'd like to finish off with, Tom?
I would just like to say thanks everyone for joining the webinar. I hope you found it beneficial, and if you'd like to watch it again, a recording will be uploaded to the NHP YouTube channel. And if you want, you can find more webinars on nhp.com.au or our dedicated YouTube channel. If you have any further questions about contact and non-contact switching and sensing devices, please feel free to reach out and contact NHP. With smarter and faster decision-making and seamless connectivity spurring new collaboration, NHP is enabling the connected enterprise. See you next time.